In this next part, I want to talk about angular momentum as a variable, because this is going to be a very important variable when we look at the hydrogen atom in look at the complete quantum treatment of the hydrogen atom. And it also leads into the idea of quantized energy levels in the old quantum theory and the so-called Bohr atom. Angular momentum plays a role in that. I apologize that I do not seem to have printed equations for this section like I did in the others, but we'll just go from there. Okay. Well, for an electron moving in a circular orbit, the angular momentum, we use the symbol L for angular momentum, is equal to the mass of the electron times its velocity times the distance. So that's our that is the kind of almost the definition of angular momentum. Now, if we're looking at this in spherical coordinates, we talk about the general motion of an electron. In spherical coordinates, we would have motion. We would separate things into angular motion and radial motion. That is, motion in the direction of the origin, and motion perpendicular to that direction. Now, in the case of the circular orbits, we have no radial motion. We only have angular motion. So the kinetic energy is kinetic energy in terms of regular linear momentum, p squared over 2 me, and p is mass times velocity. Now you can pretty easily show, and I'll just leave it to you to show that this is equivalent to writing T equals L squared over 2 me r squared. This MER squared is sometimes called moment of inertia, or I. We typically don't use that when we're talking about the hydrogen atom, but I will just mention this here. And L squared, and T in terms of that is L squared over 2I. And I just want to point out a correspondence here when we're between these two equations, one in terms of linear momentum and one in terms of angular momentum. And notice their similarity. That is, if I'm expressing it in terms of angular momentum instead of linear momentum, I replace P corresponds to L, and mass in linear, when I have linear momentum, corresponds to this moment of inertia, MER squared. So you can say it's a formula for kinetic energy is of exactly the same type, except with these substitutions, and it just depends on whether we are expressing the motion in terms of distance or in terms of angles, angular motion around around the circle. So I think you probably should be familiar with this correspondence. Now, when quantum mechanics was first being developed, there was talk about particles having wave properties, and and the idea was that in a circular orbit, if that only certain orbits were stable, and those are those where exactly an even number of particle waves fit around the circumference of the circle. And that was expressed by Bohr in this form. First of all, and again, we're going to learn more about this later, but we have Planck's constant h, and it's pretty common it shows up so much, this factor of 2 pi, that this is h over 2 pi is given this symbol h bar. And it's read like that, h, so this is simply read h bar. Okay, so that's h, or h bar, is one of the universal constants. The idea that Bohr had was that this quantum condition that I mentioned of an even number of waves fitting around the circumference of the circle was satisfied if L, the angular momentum, could only take on certain values, and n times h bar, where n is a so-called quantum number, and it can only take integer values. So L can be equal to h bar, or L can be equal to 2h bar, or 3h bar, and so forth, but no other values. And and with this condition, we find that the hydrogen atom has only certain energy levels. Okay, now with a certain amount of manipulation, and I will kind of leave it to you to do this, what we find is given by equation 11, and we find that in the handout, R equals n squared h bar squared over 4, times 4 pi epsilon naught over z e squared me. And I remind you that if I'm talking specifically about hydrogen, that z equals 1. So that says only certain radii are allowed, and and I can find them by substituting a 1 in for this n, a 2, 3, and so forth, and I'll find the allowed radii. When n equals 1, and specifically with z equal to 1, we're talking about this part of this expression, this big complicated part. That would be the radius of the lowest energy level for n equals 1 of the hydrogen atom. And this shows up quite a bit, and that is kind of universally called A0, and that's a particular length about equal to half an angstrom, and that is called the Bohr radius. So that's the Bohr radius, and you will find in any table of fundamental constants, you will find a value of the Bohr radius. Now, even though the Bohr atom is not not the accepted model, we still use the Bohr radius as an important variable, and even when we do the correct quantum treatment of the hydrogen atom, it's still very convenient to express things in terms of the Bohr radius. And then finally, the energy. The allowed energies are given by equation 13 in the document in this for this chapter, and it's a fairly complicated expression. E equals minus z e to the fourth m e over 2 h bar squared 4 pi epsilon naught squared n squared. Or, so if z is 1, this is commonly written, all this other stuff, so we'll say z equals 1, all this other stuff is some big constant, commonly called the Rydberg constant, and it's minus this constant, having units of energy, over n squared. And the values I get from this are going to be exactly identical to the correct values for the energy levels of the hydrogen atom. And then just finally let me draw a quick diagram of what those energy levels look like. And that would be, here is energy equals 0. The lowest energy level is negative energy at down here, n equals 1, and that's at minus RH. The next energy level is at n equals 2, which would be minus RH over 4. So it's like 3/4 of the way from the lowest energy level to the energy level of dissociation, 2, and that's minus RH over 4, and then and so on. 3, 4, and then they just start piling up in this region. And there's an infinite number of energy levels before I get to E equals 0, which represents the electron being removed from the hydrogen atom. So with this, I'll stop here, and I will record the last part of this that I'm going to record is an introduction to what are called atomic units, in which a lot of these equations look much simpler.